Hello बच्चों, सत श्री अकाल and namaste from my side. So this is your own physics educator Indrajit Singh welcoming you all to the Trump Ultimate Recap. Guys, okay, the last lecture was of the current electricity and that what we can say? We can say we can't say anything. Okay. So it was a current electricity. We followed the reverse engineering. Okay, through the questions we tried to cover up the each and every concept. The same thing we are going to do today. Okay, with the help of the PYQs. My moving charges and magnetism contains the very limited amount of the theories. So if we are going to understand those stuff with through the PYQs, I think it would be the great, right? Okay. So as usual, we are going to follow, as we have to complete within an hour. So we are going to follow the reverse engineering. Okay, reverse engineering, it says one numerical will come up in front of you, right, and through that we are going to solve this stuff. Okay, so guys, let's start within without wasting our time, right? Let's start within. So what will be the agenda of today's lecture? The agenda of today's lecture will be the practice question, but in another sense, right, I can write it as a practice question in summarized form. Right. Okay, so the first question, right, of the moving charges and magnetism appears in right front of you. The first question starts with, right, a particle having the same charge as of the electron moves into the circular path of the radius 0.5 centimeter. The charge on the particle is as of the electron. It means we can say it is a fundamental charge. It is moving on the circular path of the radius 0.5 centimeter under the influence of the magnetic field 0.5 Tesla. It is moving under the influence of the magnetic field, that is 0.5 Tesla. Okay, lots of data is given. If an electric field of 100 volt per meter makes it to move into the straight path, there is a presence of the electric field, okay, that forces the particle to move onto the straight path, then we need to calculate the mass of the particle, right? This question is asked in 2019 mains 9th January phase 2. So in this type of question, first of all, we have to determine what the actual data that is given. Data, the charge on the particle is as the same of the electron, 1.6 into 10 to the power minus 19 coulomb. Okay, it is moving onto the circular path of the radius 0.5 centimeter, right? Okay, radius we wrote it as a 0.5 centimeter under the influence of the magnetic field 0.5 Tesla. Now there is a presence of the electric field that forces the particle, electric field of what magnitude? Of magnitude 100 volt per meter, that forces the particle to move on the straight line. Forces the particle to move onto the straight line. Then the mass of the particle will be what? Right? The mass on the particle, it will be what? A very simplest question. Okay, see, whatever the data we have given, okay, it is used. Now what the question demands to calculate the right mass of the particle. Now what will be the trigger point to solve this question? First, under the influence of the magnetic field, under the influence of the magnetic field, right, it moves into the circular path. This will be our first trigger point. Under the influence of the magnetic field, right, 0.5 Tesla, and the second is it moves onto the straight line. These two statements would be the trigger part to solve this question, right? The above two statements, right, will be the trigger part to solve this question. So in this case, right, I think we should give you all a time. I think we are having the countdown here. Okay, so we should all give you a time of 1 minute. Okay, why I'm giving up this time? right? I will reveal that. Okay, so try to solve this question within a less than a minute. Come on, everyone. Okay, less than approximately 32 seconds are remaining. Okay, 5, 4, 3, 2, 1. See, now what happens? First of all, the two most important theories that we are going to use within, right? Those two important theories are the first one that we have already seen. Okay, whenever the charged particle enters, right, perpendicular to the magnetic field, it moves into the circular path. The second chapter, the second session, right, whenever the charge enters perpendicular to the magnetic field, it moves onto the circular path, right? And there is the presence of electric field also. Okay, there is a presence of electric field also. It means that QE is the force by the electrostatic field that forces, right, the particle to move onto the straight path, the straight line. It means two simultaneously phenomena are going on right now. Okay, it is two simultaneous phenomena are going on right now. So in this case, what is going to happen? First step, if into the presence of the external magnetic field charged particle, a point charge enters, right, then we have seen that the necessary centripetal is only the force that is going to provide the magnetic one. The necessary centripetal force is going to provide, magnetic force is going to provide the necessary centripetal force, right? And charge is going to move onto the circular path. This thing we have, this formulations we have seen into the theoretical part. So it is mv square by r, that is equal to qv into b. So here we are going to have mv by r, that is equal to q. Can I consider this as equation number 1? Yes. Now what happens? Into the influence of the electric field, it moves onto the straight line. Into the influence of the magnetic field, it moves, electric field, it moves into the straight line. So this is the second phase of the question, in which we are going to, if particle is moving onto the straight line with the velocity v, and in that the electric field and the magnetic field both are present, right? Okay, the electric field suppose in this direction, right? Magnetic field is in this direction. Let's have the clear picture of that, right? Okay, suppose, see, this is the velocity of the particle. Okay, so our first condition is satisfied. Okay, velocity is perpendicular to the magnetic field, obviously it is going to follow the circular path. Now what happens? There is a presence of electric field also that then forces the particle to move onto the circular on the straight line. Okay, so this is into the negative z direction, this is into the b, positive y and positive x. This kind of the situation appears. So this kind of the situation only appears when E by B ratio is equivalent to V. When the electric field and the magnetic field ratio is equivalent to the velocity of the charged particle, then and then this kind of the situation appears. Right? This thing again you are going to see into the dual nature of the radiation and the matter and into the electromagnetic waves. Okay. So can I name it as a question number 2? Yes. Can I replace 2 in 1? Okay. Can I replace question number 2 into the question number 1? Okay, we did that. Okay, so mv by r, that is equivalent to q of b. So m into what? E by rb, that is equal to q of b. So what is the mass? It is q b square r whole divided by electric field. Charge is 1.6 into 10 to the power minus 19, right? Magnetic field, it is given as 0.5 Tesla, right? So it is 0.5 into 0.5. Okay, the radius it is given as 0.5 centimeter. So it is 0.5 into 10 to the power minus 2 whole divided by electric field, it is given as how much? Right, 100 volt per meter. Okay, so here mass we are going to have 1.6 into 10 to the power minus 19, right, into 0.5 cube into 10 to the power minus 2 whole divided by 100, right? So here the mass is approximately going to be a 1.6. It is nearby. This is going to be 2. Okay. Okay, let's have it. Let's evaluate it separately. Mass 1.6, half of 1.6 is 0.8, right? 0.8 into 0.5 square, right? So this is 10 to the minus 21, and so it is 10 to the minus 23. Again 0.4 into 0.5 into 10 to the power minus 23. Okay, so again this is going to be 0.2 into 10 to the power minus 23. M is equal to 2 into 10 to the power minus 24 kg. This will be the mass of the charged particle, right? This is the mass of the charged particle. This is how things are going to get resolved. This is how things are going to get resolved. Yes or no? Okay. So here 2 into 10 to the power minus 24 kg. The fourth is a perfect answer for this specific question. The fourth is the perfect answer for this specific question. Let's move on to it. Okay, so now this is a very awesome question that has been asked into the 2001. Again, on the basis of the concept, the charge that is entering inside the external magnetic field. Let's move on to the question. Okay, the first important thing that I want to discuss with you all, that why I'm giving a 1 minute live. Actually, this is already into the recorded mode, so you can have the pause it to you can pause the question and you can just try to solve it. But why I'm giving you all a minute? The reason behind it is, right, I want you should all have a habit of reading the entire question and solving it within a minute. And this is not a one-shot procedure. That takes time, right? It comes with the practice, with the lots of practice. Solving the JEE based question or NEET based question entirely, reading and solving it within a minute, with a time span of minute, it is not as easy task as what you all are thinking. Okay, it needs a regular habit. Okay, if you have solved more than 200 and 300 sums, right, continuously within the less time of a minute, right, per question, then and then you are going to have the confidence into an exam, right, and you're going to crack the environment, the exam environment, right? So for that reason, I'm giving you all a minute so that you should all, right, here the 1 minute countdown is there. You have to read the question, you have to try to solve it, and when we are going to see the solution, just analyze at what point you committed a mistake, note it down. It shouldn't get repeated. Two particles A and B of masses Ma and Me respectively, having the same charge, see, mark my words, having the same charge, are moving into the plane. A uniform magnetic field exists perpendicular to the plane. Dot 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 dot, it is given. The speed of the particles are Va and Vb respectively, and the trajectories are shown into the figure. Then we have to select the correct option. Okay, we have to select the correct option, yes or no. A simple that data that has been given. First of all, let's allow me to have the data. Okay, the trajectory of the two particles are given in data. The trajectories are drawn, right? Okay, masses are mentioned, Ma, Mb. Velocities through which they are entering perpendicular to the magnetic field are mentioned, Va and Vb. Now we need to find the correct relation in between the momentum of the particles. Cool. This is of the B1 and this is of the A1. Okay. So this time also let's give you all a minute to solve this stuff here. Okay. So your minute starts here. Okay. So let's have the detailed analysis of the it we have solved within a minute. So first of all, let's take on the paper. Right? Without paper, it is difficult to understand this question. Right? Without paper, it is difficult to understand this question. Okay. This is a paper we have taken. Now magnetic field is in dot. So it means it is pointing outwards. Right? Magnetic field is pointing outwards like this way. Right? Magnetic field is pointing outwards like this way. Okay. I'm just noting out like this way. I'm covering up the boundary point and the mid part I have kept for the explanation purpose. Like this way it happens. Okay. Now see here, the two charged particles are entering into the external magnetic field and the trajectory they are following is like this way. Okay. This is a trajectory of B and this is a trajectory of A. Okay. So can I say this is the radius of the A and this one is the radius of the B. No data about their radius is mentioned into the question. No data about the radius, it is mentioned into the question. So simply the trigger point to solve this question is what? The trigger point to solve this question is the charged particle is entering into the external magnetic field. They are following the circular path. It means somewhere the necessary centripetal is provided by the magnetic force. Right? If this happens, then and then the second case of whenever the charge enters the external magnetic field. Second case. Okay. And even the second lecture of this chapter. If this is happening, then and then this case is possible. So it means that mv square by r, right? It is equal to qv of b. One v get cancelled, right? So it is mv by r, that is equal to q of b. So mv you are having qb into r. This is the expression that we have reached. Okay. This is the expression that we have reached. Now what happens? There is a very simple explanation to this question. The charge of the particle is the constant value, right? The magnetic field of the surrounding area is also the constant value. So it means that the mass and the velocity, the product of the mass and the velocity of the particle is directly proportional to its radius. The product of mass and velocity of the particle is directly proportional to its respective radius. So it means that one thing is common, one thing is fixed, right? The fixed thing is all about, right? The particle that is having the trajectory of the highest radius will be having the highest value of the momentum. You can see now they are into the direct relation with respect to each other, na? Okay. So the radius, okay, of the trajectory that is of the higher value as compared to another will be having the highest momentum. So here you can say the radius of the A, okay, it is greater than radius of the B. The radius of the A, it is greater than the radius of B. So this and this relation simply defines that, okay, that M of A, V of A is obviously greater than M of B and V of B, right? This will be the perfect relation, okay, and this will be the perfect answer to this specific question. Okay, this will be the perfect answer to this specific question. The radius of the upper trajectory, I'm sorry, this is RB, this is RA, sorry for the small mistake. The radius of the upper and the lower one, the upper one is a higher, okay, lower one as compared to the lower one. So in this case, from this relation, radius is directly proportional to the product of MV, that is linear momentum, okay, and here this is going to be the perfect result for it. So here MAVA is greater than MVB. This is the perfect answer for this specific question. Okay. The B is the perfect answer for this specific question. The PYQ, awesome PYQ of the 2001. Now, let's move on to the next question onto it. Oh, awesome thing has came in from the question that has been asked from 2019. Okay, 12th April phase 2. Find the magnetic field at a point P due to a straight line segment AB of length 6 centimeter carrying a current of 5 ampere. Wire is there, right? This is 6 centimeter. The hypotenuse is given as the 5 centimeter. We need to calculate the magnetic field of the point P. Okay, let's note down this data. What is the agenda? To calculate, right, magnetic field at point P, right, due to the straight line segment. Second, length of the segment, it is given as 6 centimeter. The current value, it is given as 5 ampere, right, and rest of the right, the permeability value is given. Okay, so what will be the trigger point to solve this question? I'm going to give you all a minute, right? Before that, we are going to discuss about the trigger point. Okay, trigger point would be by seeing this data and what we need, immediately we will all should get a click that we are going to follow the Biot-Savart's law. One of the most important general equation of the Biot-Savart's law that we have seen before. Right, one of the most important equation of the Biot-Savart's law that we have seen before. Okay, so one of the application of the Biot-Savart's law, and obviously this time also I'm going to give you all a minute so that you should solve this question within it. Come on everyone, I'm moving aside. Okay, you can have your time. Less than 7 seconds remaining. Come on everyone. Okay, the one of the most important applications of the Biot-Savart's law, right, one of the most important applications of the Biot-Savart's law, right, that equation of the magnetic field at the perpendicular distance of a finite length current carrying conductor. After Biot-Savart's law, we have seen the first equation, current carrying conductor, Biot-Savart's law. The very first equation, it was mu 0 I whole divided by 4 pi perpendicular distance d sine of theta 1 plus sine of theta 2. Right now I'm only moving forward to the magnitude. Okay, by the end we will discuss the direction. Okay, by the end we will discuss the direction. So it's mu 0 I whole divided by 4 pi d sine of theta 1 plus sine of theta 2. Now here, this will be the theta 1, this will be theta 2, but this we are not aware of. Okay. So can I say this is 6 centimeter? If it is dividing right equally into the two parts, then this will be 3 and 3. Okay. If this angle is making 90 degree, this side we are having 90 degree, this side we are having 90 degree, right? So can we say that the value of this sine theta 1, that we are going to get it as 3 by 5. The value of sine theta 2 from the different triangle, again we are going to get as 3 by 5. Okay. And the perpendicular distance is obviously 4 centimeter, right? Okay, if we are using the Pythagoras theorem, then this perpendicular distance is going to come upon as the 4 centimeter. So D, we are going to take it as the 4 centimeter. Okay, so these are the two most important data that we are going to use. Okay, from the triangle and the simple Pythagoras we have used. From the triangle and the simple Pythagoras that we have used. Okay. So B is equal to mu 0 I by 4 pi d. Okay. So mu 0 I 4 pi into 10 to the power minus 7. What is the amount of the current flowing? That is equivalent to 5 ampere whole divided by 4 pi into the perpendicular distance is d. So it is 4 into 10 to the power minus 2. Actually it is in centimeters. So we have written into the meter. Okay. Sin theta 1 value is 3 by 5. Sin theta 2 value is 3 by 5. Okay. So this is going 4 pi is going to get cancelled. So it is 5 by 4, right, into 10 to the power minus 5 into 6 by 5. So this 5 is again got cancelled. Okay. So it is equal to 3 by 2 into 10 to the power minus 5. Okay. So the net magnetic field you are going to get it as 1.5 into 10 to the power minus 5 Tesla. Right. Okay. So this will be the solution. Right, this would be the solution. Yes or no? Okay. So this equation reminds us about the first application of the Biot-Savart's law. The equation reminds us about the first application of the Biot-Savart's law. Right, the one of the most of the important applications. Right, and on basis of this, the magnetic field has, because of the infinite length current carrying conductor has been defined. I told you all I taught that if it is extending up to infinity, then theta 1 and theta is going to, the side which is extending up to infinity, the side which is extending up to infinity, it makes an angle with respect to the point as pi by 2. Like this way, na? Suppose it extends up to infinity, like this way it is moving on. Right? Yes or no, guys? Okay, yes or no? Let's move on to the next question. Oh, again the equation of the one of the application of the Biot-Savart's law came. See how Biot-Savart's law is quite important. I heartily apologize, I lost my pen. यार हर बार मेरे हाथ से पेन गिर जाता है. Okay, again another application of the Biot-Savart's law came. See, this is again the previous question was asked in 2019 12 April, here also 2019 9 Jan, the second, right, the first phase 2019 mains examination. Okay, this is also one of the applications of the Biot-Savart's law. The current loop having two circular arcs. This type of the questions we have seen. You can just check it out, the second or third, yes, third lecture. The Biot-Savart's law is the third lecture, the third presentation lecture of this chapter. Okay. A current loop having the two circular arcs, they are joined by the two radial lines. Each carries this side the current is in this direction of the 10 ampere and this side the current is in this direction of 10 ampere. What will be the net magnetic field at the point O? They are saying it should be closed to. It means somewhere, right, the fraction might be coming up, but we are going to analyze it. So first of all, whatever the data that has been given, it is given as two circular arcs. Okay. Second data of the current, it is given that is 10 ampere is flowing through which, okay, the arc is subtending the 45 degree of the angle, right? What we need to calculate, we need to calculate the net magnetic field. We need to calculate the net magnetic field. So two circular arcs, 10 ampere, 45 degree, right? And we need to calculate the net magnetic field. Okay. So hint I gave you all. It's one of the application of the Wyatt-Savart's law. But I think you need 1 minute to solve this stuff. Come on, everyone. Okay. What thing we are going to use in it? We are going to use the magnetic field equation as because of the arc mu 0 I whole divided by 4 pi r into theta. Okay. The direction will differ, but we are going to have a magnitude. We are going to deal with the magnitude. So, see, basically here we are having the two arcs. This is arc number 1 and this is arc number 2. If you want to calculate the net magnetic field, right, then we can say it is B1, right, plus B2. Magnetic field is because of the arc 1 plus magnetic field is because of the arc 2. This is a solution, right? Magnetic field is because of the arc 1 plus magnetic field is because of the arc 2. Now see, if I'm talking about the arc 1, right, okay, I'm just keeping my right hand here, okay, I'm just keeping my right hand here, hold on, okay. Now, magnetic field is coming out as because of B1 from this point, right, magnetic field is coming out, out means dot. So magnetic field, it is mu 0 I whole divided by 4 pi r into theta. 1 is dot plus magnetic field is because of the second. I'm into the direction of the current. I'm keeping up the thumb using the right hand rule. The magnetic field is inside. So as because of 2, the magnetic field we are going to have it the inside, right? So it is cross. Okay, I told you on to the previous presentation lectures, the third one. Dot means positive K, right? Okay, unless it is mentioned. Generally, we are taking this as X and this is Y because this is a 2D plane, right? If it is just mentioned somewhere, then you have to just check it out. Okay, but in this question, it's not mentioned. So directly, we are taking this is X axis, this is Y axis. Pointing out, it means positive K. Directing inside, it means negative K. So here, this will be mu 0 I whole divided by 4 pi r into theta, negative K, right, plus this is R1 mu 0 I whole divided by 4 pi r2 theta, and this will be positive K. I'm sorry, this will be the positive K and this will be negative K, right? So the radius of one is 3 centimeter, radius of second it is 5 centimeter. Radius of one it is 3 centimeter. So here the net magnetic field, right, we are going to have it as, okay, 4 pi into 10 to the power minus 7 whole divided by 4 pi into r. For first it is 3 centimeter, 10 to the power minus 2, and that is pi by 4. Okay, and that is positive of K plus, right, this is what For the first, the radius is 3 centimeter. For the second arc, the radius is 2 centimeter. Dot means positive k. Okay. For the second, 4 pi into 10 to the power minus 7 whole divided by 4 pi into 5 into 10 to the power minus 2 into pi whole divided by 4. Right? And this is negative k. Okay. So what will be the value of the net magnetic field that is coming up as 4 pi cancelled, 4 pi cancelled. Okay. So it is pi by 12, right? Just hold on. It's pi by 12 into 10 to the power minus 5 minus pi by 20, right? Into 10 to the power minus 5. This is plus k. Okay. So I am taking pi into 10 to the power minus 5 as a constant value. Pi into 10 to the power minus 5 as a common. 1 by 12 minus, right, 1 by 20 into the positive k. Okay. Now it happens like the net magnetic field. Okay. It is pi into 10 to the power minus 5. Okay. So this is 20 minus 12. So it is 8 whole divided by 12 into 20 into positive of k. Okay. So this is going to be 4 2s are 4 3s are 2 10s are, right? So this is going to be pi by 3, right, into 10 to the power minus 6. Okay. This will be the net magnetic field. Okay. Into plus of k. Okay. Net magnetic field into plus of k. So I think they are saying close to. So I think the close to, it means the 1, this 1 into 10 to the power, say it is 3.14 divided by 3. So it is, I think, close to 1 into 10 to the power yes, 10 to the power minus 5. Right, I think there is a misprint. Okay, misprint. So this is a perfect answer for this specific question. I think there is a misprint. It's okay. Okay, now let's move forward, right, to the next question. It is a misprint. This would be the perfect answer for this specific question. Now, from the Biot-Savart's law, we are jumping right to the question, the 2016 mains. Right, we are going to use the Biot-Savart's law, but this time into the different way, and then we'll jump on to the next question. Right, then we'll jump on to the next question of the wires. Two identical wires A and B, each of length L, carries the current I. Wire A is bent into the circle of the radius R and wire B is bent into the form of the square. One wire is bent into the form of circle. Second wire, it is a form into the bent into the form of square. If BA and BE, BA and BB are the magnetic field values at the center of the circle and the square, then ratio of BA by BB will be what? One of the applications of the Biot-Savart's law. Two of the applications of the Biot-Savart's law. Wire, it is transformed into the form of circle. Wire, it is transformed into the form of square. Okay. The wire is of the each length. The square side is A. That is obviously going to be L by 4. Okay. And the radius of wire is R. Okay. So this R is going to be, let's say the circumference of the circle is this. Okay. So this two most important relation again we are going to use. Right. So I think let's give you all a minute. I have given the hint. This is a bit lengthy question. 15 seconds remaining. Come on, everyone. Okay, one, it is bent into the form of the circle. The second, that is bent into the form of the wire. Right now, okay, so this side, okay. Magnetic field is because of this circle, and obviously at the center it is defined as mu 0 I whole divided by 2 of R. So for the first, the wire that has been transformed, right? So it is mu 0 I whole divided by 2 of capital R. The wire, the equation of the Biot-Savart's law, right? This equation has been evolved from the arc only. This thing we have discussed into the presentation slides, into the presentation, the third chapter, the third lecture. Okay. Now one that has been transformed into the square of the side A, right? So the magnetic field is because of the B, that is equal to mu 0 I whole divided by 4 pi A into sine of theta 1 plus sine of theta 2. Okay. But this is for the one side. We need for the entire square. So 4 will be multiplied. Okay. 4 will be multiplied. 1, 2, 3, 4. If I'm talking about the direction of the current, let's say this is the direction. So as because of the each and every, using the right and thumb rule, as because of the each and every segment, the magnetic field we are going to get is a cross. Right? Magnetic field we are going to get it as a cross. Right now I'm dealing with the magnitude only. Okay. Why I have shown it as a cross? Because many students might be into the thought how it got multiplied with the 4. This is the magnetic field for the first segment, cross. Second segment, cross. Third segment, cross. Fourth segment, cross. All will be added into the equation of the net magnetic field. All will be added into the equation of the net magnetic field. Yes or no, guys? Okay. So we need to evaluate this B part. 4 into mu 0 I whole divided by 4 pi A. Now for a square, right, angle is always 45. So it is sine of 45 plus sine of 45. So B of B, that is going to come upon as 4 into mu 0 I whole divided by 4 pi of A. Okay, this is 1 by root 2, 1 by root 2, 2 by root 2, this is root 2. So this is the magnetic field as because of the 1, I am naming it as a 1. This is magnetic field as because of the 2, I am naming it as a 2. We need to evaluate and calculate the ratio of 1:2. Okay, we need to evaluate the ratio of 1:2. So here, mu 0 I whole divided by 2 of R whole divided by, this is for 1, mu 0 I, the 4 into mu 0 I whole divided by 4 pi A into root of 2. So mu 0 I is going to get cancelled, right? 4 is going to get cancelled. So B A by B, right? So this is going to be mu 0 I and 4 is going to get cancelled. Okay, this is root 2. Okay, 2 root 2 R into pi of A. Okay, 2 root 2 R into pi of A. Now we are going to replace A and R. Okay, the thing that we have decided, right, because we need an exact ratio now. So anyhow we have to replace A and R. If we need a ratio into the numerical form, right, anyhow we have to replace A and R. So how we are going to replace A and R? A is nothing else but L by 4. Pi into L by 4 into 2 root 2. R, it is replaced as a circumference of the circle, that is 2 pi R is L by, right. So R is equal to L by 2 pi. The same thing that we are going to replace it here. Okay, L by 2 pi. So it is L into 2 of pi. Why I have replaced A in terms of L? R in terms of L, so that easily we can cancel out the effect, right? So this is again 2 will get cancelled. So it's pi square whole divided by 4 root 2. This is the ratio of the magnetic fields at the centers, right, of the square, okay, in the circle and the square. I'm moving aside. If you want to have a 10 seconds to, right, have a countdown of it. Right, you want to have a screenshot or then you note down any mandatory things, you can. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Right? So it's pi square by 4 root 2. I think we did a mistake somewhere. Pi square by 8 root 2 is coming by 4. Somewhere we have done any kind of a mistake. Okay, mu 0 I whole divided by 2r. Okay, it is a circle, it means it is a circumference. So it's L by 2 pi. Okay, mu 0 I by 2 are at the center. Okay, 4 mu 0 I by 4 pi a. So it is, okay, in this calculation we have done the mistake. Right, in this calculation we have done the mistake. So I think allow me to check this stuff. Right, allow me to check this stuff. Right, again let's check it out, the data. Okay, now the two identical wires, okay, allow me to check this stuff. The two identical wires, right, one of radius a, right, and second is of the each length. Okay, we have done a mistake. So yes, same into that part. A is equal to L by 4 and okay, R is equal to L by 2 pi. It's cool. Okay, we have done into that part. Okay, yes, 8 root 2 is going to come. We have done the mistake into that part, right? It will be 4 root 2. Okay, 8 root 2 is going to come as the perfect answer. Okay, 8 root 2, pi square by 8 root 2. Small mistake has been done. Okay, it's okay, it happens. Sometime it happens, right? And do the calculation of this field separately, you can just check it out. Okay, a small mistake has been done because here 4 of the sides will come and A is also going to come upon as L by 4, right? Okay, A is also going to come upon as L by 4. So as of that reason, it would be 8 root 2, right? Okay, okay, it happens. Okay, now let's move on to the next question, right? Small question mistake happens. 2019 mains 8 April. Now this time we are moving forward from the Biot-Savart's law, right, to the torque. A circular coil having the n turns and the radius r carries a current I. It is held into the xz plane. Circular coil is kept into the xz plane. The magnetic field is into the I direction. The torque on the coil due to the magnetic field will be what? Allow me to represent this stuff. This is x-axis, this is y-axis, and this is the z-axis, right? The coil is kept into the xz plane. Magnetic field is directed into the x. Right? First of all, into the previous question, I told you all we have done this mistake in this part, right? So try to just evaluate it. Okay, 1 4 we have missed. Okay, if you want to solve it again, then we can V is equal to 4 mu 0 I whole divided by 4 pi into perpendicular distance, right? And that is 1 by root of 2 plus 1 by root of 2. So B, this is 4 is going to get cancelled. So mu 0 I, again it is going to be 4 into root 2 pi of A, right? Okay, to root 2, that is 2 by root 2, and okay. So 4 mu 0 I, right? Okay, divide by 2 root 2. Okay. Right. Why they have taken as just hold on, guys. Right, mu 0 I whole divided by okay. Right, 1 by root 2 1. Ha ha ha. Okay. Here it will be A by 2. I'm sorry. We found a mistake. The exact mistake. Right. The square is there, na? The exact mistake we found. Here the square is there, na? The entire distance is A. But obviously we are going to take this, na? Because this perpendicular distance is A by 2. Right. So actually this would be A by 2. Okay. Okay, so as of that reason, finally we are going to come. See, this is the square. What mistake we did? We did the perpendicular distance into the bottommost part as A. Actually, it is A by 2. Right? Because its entire length is A, na? But we need to find out this perpendicular distance, na? So that is A by 2. This mistake we have done. Okay, we cracked it up. Okay, heartily apologize for that. The answer is going to be pi square by 8 root 2. Okay, now we are moving forward to the next question. Okay, the coil is kept like this way. Coil is kept like this way, right? Magnetic field is directing towards the positive I direction. Okay, magnetic field is directing towards the positive I direction. Okay, now what we need to calculate? We need to calculate the torque as because of that. A very simple calculation in the formula based question, right? A very simple calculation. Okay, so first of all, let's allow me, right? Whatever the data, we have to use it up. Okay, first, the magnetic field is into the I direction with the magnitude B. Okay, coil is placed in XZ plane, right? Okay, and we need to calculate the torque. So it means that simply we have to use the formula of the torque. That's it. Simply we have to use the formula of the torque. Yes or no, guys? Right? So as usual, let's give you all a 1 minute, which is a direct formula based question. So we can give you all a minute to solve this stuff, right? And easily you can do that. So moving aside into the see, this question is just a matter of 15 seconds, right? And some of the students might do orally also, but it's okay. You can move on to it. Less than 20 seconds remaining. Come on, everyone. Okay, so yeah, we need to calculate the torque. What is the torque formula of torque? Bina. This is XZ plane, right? Coil is kept. Okay, coil is kept into the XZ plane with the radius of R. Okay, magnetic field directs in this direction. This is the direction of the magnetic field. Okay. So what will be the formula of the torque here? Okay, so the formula is torque is B na, right? The formula of the torque, that is equal to B na sine of theta. Obviously this area vector is directing into this direction, right? So this B na sine theta is going to be 90 degree. Here the theta is going to be 90 degree. So torque, that is equal to B I N A. Okay, so what is the area of this loop? Area of this loop, we can say it is 4 pi r square. Okay, replacing it here, you are going to get the formula of the torque as B I N into 4 pi r of square. Apart from this, are we having any kind of a thing that we can replace it up? No. So here the formula of the torque is going to come upon as B I 4 pi r square N, right? Or NB nib 4 pi r square, right? Nib 4 pi r square. Okay, so I think yes, the B is going to be the perfect answer for this specific question. B is going to be the perfect answer for this specific question, right? Yes or no? Okay, B is going to be the perfect. So now let's move on to the next question. Okay, now this two long parallel wires, I'm going to give you all this question into the homework, right? I'm going to give you all this question into the homework. The two thin long parallel wires separated by the distance B. Two long wires are there, they are separated by the distance B, right? Are carrying a current I ampere into the each. Okay, what is the magnitude of the force per unit level? In 1986 it was asked indirectly. Okay, one question I have to add, you have to just calculate the magnetic field as because of the center also, huh? As because of this two wire, you have to calculate the net magnetic field at the center. Okay, this thing we have done into our presentation lectures, and many times this has been asked into an examination. Right? Okay, so this is the homework from my side. I will be waiting for all of your comments beneath the video. Okay, apart from, so it was all regarding the moving charges and magnetism, and then I will have the conversation with the team. We can do much more for you all. Okay, but for this lecture, let's keep that much enough for today. Okay guys, so it's time to go. Okay, again we will come back with the next lecture. This is your own physics educator Indrajit Singh signing off from the desk. Bye bye. Sat Sri Akal and Namaste from my side. Bye everyone. Stay at home, stay safe, stay healthy amidst this pandemic, and take care. Bye.